You ask a question to a modern search engine and receive a concise summary that sounds authoritative. It feels helpful. It feels complete. But recent research suggests this convenience comes at a steep price. A study auditing Google's AI overviews and featured snippets found that in high-stakes domains like baby care and pregnancy, the AI provided inconsistent information in nearly a third of cases. Worse, critical medical safeguards were missing in over 80% of responses. This is not just a minor glitch. It is a systemic reliability issue where the model asserts false information with high certainty, a phenomenon researchers call the confidence paradox. Here is the thing that matters most. When an AI summary lies, it often does so with a tone of absolute conviction. It does not hedge. It does not say it is unsure. It states the falsehood as fact. This creates a dangerous environment for users relying on these tools for vital health information or critical infrastructure decisions. While some investigations focused on traffic cannibalization, noting that authoritative sources like Wikipedia see a drop in visits, the core issue remains factual accuracy. The scale of misinformation is massive, with automated testing suggesting millions of false statements are generated hourly across search queries. If we accept this as the new normal, we risk building systems on a foundation of sand. So, how do we fix this without abandoning the technology entirely? The answer lies in a practical human-in-the-loop architecture. This approach forces the large language model to cite source rows before it speaks, specifically for validating machine learning pipelines and infrastructure logs. It is not about trusting the model. It is about verifying every claim against a known source of truth. Now consider this analogy. Imagine a lawyer in a courtroom. A witness can tell a story, but without evidence, their testimony holds little weight in a binding contract. In this architecture, the large language model is the witness. It generates the summary, but it must point to the specific page in the evidence file where that information was found. The evidence file is your database. The contract is your output. If the witness cannot point to the page, the testimony is rejected. This is the core of the solution. We are building a system where the AI cannot hallucinate freely because it is tethered to a structured query language database. Let us walk through how this works in practice. You start with a Python script that acts as the orchestrator. This script sends a query to the large language model, but it includes a strict constraint in the prompt. It tells the model that every claim must be backed by a row identifier from the source database. The model generates text, but it also generates a list of citations. These citations are not just links, they are specific row IDs from your SQL database. Once the model returns its response, the system does not immediately show it to the user. Instead, the Python script passes the citations to a verification engine. This engine runs a structured query language command against your source data. It checks if the row ID exists. It checks if the content in that row actually supports the claim made in the summary. If the row is missing, or if the data in the row contradicts the summary, the system flags the output. It marks it as unverified. This creates a safety net. For infrastructure logs, this is critical. When an automated system summarizes a server outage, it might say the disk was full. The verification step checks the log file row that triggered that summary. If the log file says the disk was actually at 90% capacity, but the summary claims it was full, the discrepancy is caught. The human operator is then alerted to review the specific log entry. This is a human-in-the-loop process. The machine does the heavy lifting of summarization, but the human validates the truth of the underlying data. Why is this architecture necessary for machine learning pipelines? Because models drift. Data changes. A summary generated yesterday might be accurate based on the data of that day, but today the underlying metrics have shifted. If your monitoring system relies on an unverified summary, you might miss a real alert or chase a phantom problem. By forcing the model to cite the source row, you create an audit trail. You know exactly which data point led to which conclusion. This is invaluable for compliance and debugging. Furthermore, this approach addresses the confidence paradox directly. When the model is forced to link its output to a specific database row, it is less likely to generate confident but baseless statements. The constraint of citing sources acts as a cognitive anchor. It reduces the model's tendency to fabricate information that sounds plausible but is factually unsupported. In the context of health queries or safety-critical alerts, this distinction between plausible and proven is everything. We must also consider the cost of this verification. Running a query for every citation adds latency. It requires more processing power. But in high-stakes environments, speed is secondary to accuracy. A delayed alert is better than a false alarm that causes unnecessary downtime. The system can be tuned. For low-risk queries, you might relax the citation requirements. For high-risk domains like medical advice or financial reporting, you enforce strict verification. This flexibility allows you to balance performance with safety. Another layer of this architecture involves the feedback loop. When a human operator corrects a summary, that correction is stored. Over time, the system learns which types of queries tend to result in hallucinations. It can prioritize those queries for human review. This creates a self-improving system where the verification process becomes more efficient as the model improves or as the data patterns stabilize. It turns the verification step from a static gate into a dynamic learning mechanism. The implications for infrastructure logs are profound. Imagine a scenario where your system summarizes thousands of log entries into a daily report. Without citation, the summary is a black box. You do not know which specific errors were aggregated. With the human-in-the-loop architecture, every summary point links back to the specific log line. If a trend emerges, you can trace it back to the root cause in the database immediately. This transforms the summary from a passive report into an active investigative tool. In summary, the research is clear. AI summaries are relevant but frequently lack necessary safety mechanisms and consistency in sensitive domains. The confidence paradox means we cannot trust the tone of the output. We must trust the evidence behind it. By implementing a human-in-the-loop architecture using Python and SQL, we force the model to prove its work. We move from blind trust to verified trust. This ensures that machine learning pipelines and infrastructure logs remain reliable sources of truth rather than generators of misinformation. The path forward is not to reject the technology, but to build guardrails that force accountability. Verify your data, require citations, keep a human in the loop. Until then, do not trust the summary blindly. Check the source. This is the only way to ensure safety and accuracy in an age of automated generation. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.